Since I had experiments with 3D printed material stiffness, I got some samples from filament manufacturers to test them products. One of its descriptions of the performance caught my attention. So why not give some tests for this Igumid P150 engineering plastic? Hi, welcome to Slow Engineering. I'm David. Igumid is a company that provides various engineering plastic filaments. They focus on wear resistance, self-lubricating, and high strength for most filaments. For structural design, the samples I got are the Igumid P150. It prints at 250 to 270 degrees Celsius on the nozzle and 50 to 70 degrees Celsius on the bed. The thermal resistance is 100 degrees Celsius continuously and 120 degrees Celsius in a short period. This material might be similar to the PA12CF I introduced previously, having almost the same printing temperature range and thermal resistance. P150 material emphasizes its flexural strength, which can reach 87 MPa along the printing surface orientation. As an isotropic material, the elastic modulus is 4700 MPa. These types of fibered materials are typical for structural parts. So what about the P150's performance in flexural tests and creep tests in isotropic 3D printed parts? If you want to know the experiment setup, please check the link in the description to watch the previous video. The flexural tests and creep tests are around deflections on the specimens. Further, the deflection in the flexural test can be calculated into the flexural modulus and flexural strength. I printed some specimens at 260 degrees Celsius with the bed temperature at 60. Other settings are the same as the specimens I tested before: 4 top layers, 3 bottom layers, 4 walls, and 100% infill with the light patterns in Cura. Based on the experiments of the last PA12CF tests, I also prepared 2 groups of both dry and wet setups. The printed specimen stays in the dry box to prevent absorbing moisture as a dry group. And for the wet ones, put them into water 24 hours before testing. For the first flexural test with low scale in 500 grams, from 0 to 3 kilograms. The diagram shows both the dry and the wet groups deflections compared with other materials. The result is surprisingly different from the PA12CF I tested before. Both groups perform low deflections on lows and even have lower slopes than PLA. In other words, they have higher stiffness than PLA, unlike the PA12CF, which performs poorly when getting wet. P150 still holds its properties well. Both features make this material ideal for the parts that need stiffness. The second test are the creep test. It is a test to have a constant low for a while, then measure the deflections as well to see how the materials hold shapes. Based on these results, loading application materials can be chosen without being concerned about deformations. The test is to hang a 500-gram bottle on the specimens for 3 days and measure the deflections after 72 hours of loading. As the diagram shows, the dry samples share the same results as the wet ones. It means moisture is not a critical factor in creep. The deflections are incredibly lower than other materials, which again make it suitable for frame structure. As a structural material, P150 has a role to play. It provides not only stiffness but also low creep performance, making this lightweight material become a choice for frames and structural parts. Here are the tests for the Igumid P150. I hope you enjoy. Like, share this video and subscribe to this channel if you think it's helpful. Or consider checking out the link in the description to get more detailed data about this material on Patreon. Thank you for watching and see you next time.